Okay, hello everybody. We are back for another review session here. So, we're going to take a look today at lecture 8. We're going to look at ligand binding, and we're going to look at these things here. We're going to look at ligand, just ligand binding in general, O2 for myoglobin, and then O2 binding and release for heme, right? So, hyperbolic, so this is only one binding site, and sigmoidal is multiple binding sites. We got cooperative binding, so we'll take a look at those today. In the last review, we talked about things like TM and denaturant 50. These are things where, I'll talk about this later, a little bit of cooperativity. But the idea that, the amount of concentration of denaturant or temperature required to fold the protein by 50%, right? How do proteins find their native folds? They basically go through these different structures. They fold into these secondary structures, and these structures combine to make the final structure, right? We talked about chaperones and how they help uh, with making proteins that are not what they're supposed to be doing into proteins that are supposed to be doing what they're supposed to be doing. Right? They kind of fix broken proteins. We've got heat shock proteins, and we've got this chaperone proteins, GRO-EL, GRO-ES. Okay, so what we want to talk about, right, is we've got this idea of, proteins are not static structures. They are moving and changing depending on what binds to them. Um, so basically what I want to get into your head here is this thing about how structure impacts function, right? And structure is actually altered by binding of certain things, which inherently alters function, right? So proteins undergo conformational changes, right? And that impacts their functional properties. So, like, an example of this is CTP synthase, right? So you have the apo version, which is the version of the protein without anything bound. And then when you bind something, right, it actually changes the conformation of the protein, right? And that allows it to do its function, right? What it might do is it might change it so that more things can bind to it. It might change it so that the actual function of the protein can be carried out, right? So, like, for example, a lot of things like need ATP to do their function, right? The binding of ATP and the hydrolysis of ATP change the conformation of a protein, right? So that it can actually do its job. So, like, myosin is an example of that, right? Myosin is a motor protein. The binding and hydrolysis of ATP changes its conformation so we can have muscle contraction, right? And cross-bridge cycling. So things like that, right? So ligands are like, there's many different things to be ligands. Ions, DNA, RNA, other proteins, a whole bunch of things that can be ligand. Apo is just the structure without a ligand, and holo is the structure with the ligand. So you'll hear things like apo enzyme, holo enzyme. Apo enzymes without the ligand, holo enzyme is with the ligand. In the case of an enzyme, it's actually substrate technically, right? But yeah. The structure depends on conditions like the presence of a ligand, right? Are there other things bound? Does the binding of one ligand affect the binding of another ligand, right? Post-translational modifications. Is there phosphorylation? Does that affect the binding of certain ligands, right? So you'll see when you eventually get into like the glycogen pathway that phosphorylation and dephosphorylation affects the structure of those enzymes, which affects their conformation changes, which affects their function, right? Here we've got just this basic idea that there's a protein and there's a ligand, and those eventually will associate to form this protein-ligand complex. We can do a simple thing, right? Similar to how we kind of look at Ka, right? Like an acid dissociation, right? Like, we do products divided by reactants, right? We do the same thing here, right? If we're trying to look at the association constant, we're going to look at the production, how much of this is present versus how much of this is present. And that'll tell us the affinity of any given ligand, right? So if we have a lot of this substrate here, a lot of this complex and very little of this in our solution, we know that this enzyme or protein has a very high affinity for its ligand, right? On the other hand, we have Kd, which is actually what we generally use for like measuring affinity. It's the opposite, right? We're measuring if there's a lot of this and little of this, little of the protein ligand complex and a lot of the protein and ligand separately, we know that there's not a very high affinity for our protein, right? And these are measured in concentrations, right? So basically what this tells us is, right, that is that if we have a low KD, right, we actually have a very high affinity, because that would mean that we have a lot more. We have low KD, that means we have a lot of this protein ligand complex and very little of this protein and ligand separately, right? So on graphs, if you're looking for affinity and you're looking for KD, right, lower KD means higher affinity, right? And here we get to this idea of fractional occupancy, right? You don't need to know how all these equations work. Just know this. Memorize this, because this will show up, right? So fractional occupancy, right, is some value, right? And the KD specifically is the point at which fractional occupancy is 0.5, right? And it's going to be some concentration, right? So you're going to be given some amount of ligand, right? If you know how much ligand you're at, and you know the KD of a reaction of the enzyme, right, you can figure out how many sites are occupied, or how many of the enzymes are occupied, I guess, right? The fractional occupancy of this protein, right? What does KD tell us? Like I said before, it kind of tells you about the strength of a ligand binding, right? Smaller KD is better binding, right? That makes sense, right? If we have the KD is the protein concentration, the ligand concentration, divided by the protein ligand combination, right? If we have higher protein ligand and lower protein and ligand separately, we know that this is the favored form, and we have a lot more protein ligand, which makes sense that KD would be smaller, right? Because if the denominator is bigger than the numerator, this goes down, right? So we can look at this, like, what is the fractional occupancy for calmodulin when it's this concentration or this concentration, right? And you can go through these if you'd like, but all you have to do then is use this equation, right, and calculate those. So now we move on to globin, so myoglobin and hemoglobin. So myoglobin is not cooperative and only one subunit, if I'm not mistaken, and hemoglobin is multi-subunit. They're homologous proteins, so they are similar, but they are not the same, right? And the interesting thing to know is that myoglobin, right, is one polypeptide chain with 8 alpha helices and one heme group. This is different from a little bit different from hemoglobin, which we'll talk about in a second, right? And the common fold amongst globins is this alpha helix, right? You can see the alpha helix here, alpha helix here, alpha helix. There's a bunch of alpha helixes. There's not very many beta sheets usually. And the O2, right, is basically associating with this positive iron. You might like, why is it associating with iron? Well, we have a lot of iron in our body, and the oxygens have a lot of electrons on them, right? And the electrons are attracted by the positive charge of the iron, right? They're also attracted to histidine, so that's something to keep in mind. Which is actually also why histidine is very important. And you'll see later that pH is actually very important for how our blood is able to hold oxygen. So when it comes to KD, we actually have a very special version when we are looking at the occupancy for hemoglobin and myoglobin, right? And we use different terms for it. So this is the expression for the association and dissociation. You can imagine there's like a Ka up here, right? Of myoglobin, right? So we've got separated myoglobin O2 versus combined, right? If you do the KD for this, the KD is about how much of it is dissociated versus associated. So this over this as a fraction, which is what this is showing, right? And so we now have we can use this to create a similar to the ligand formation we have up there, like Y equals ligand plus KD, and these are obviously concentrations. I'm just right. This is the exact same form, right? The only thing that's different here is that O2 is a gas, right? So we can't just use concentration of O2. We have to use partial pressures. So we change it to PO2, right? And we've decided, that instead of using KD for the attachment of O2 for this point, that this 50% mark, this 50% occupancy mark, we're going to use P50 instead. So this is for how you calculate the occupancy of hemoglobin if you were given the partial pressure of oxygen in the environment, and you were able to figure out the P50 or the KD of the oxygen to hemoglobin interaction. All this slide is trying to show you is that when we do the math for myoglobin, right, it has a very high affinity, right? So you know that smaller numbers, right, for KD, or in this case P50, means very high affinity. And for myoglobin, it's 0.26 or 0.003 atmospheres. This is ridiculously strong. Okay, for example, like just as a marker, right? So there's about 120 millimeters of mercury of oxygen in the atmosphere. I can't remember the exact number. I think it's like 0.2. So like 0.2 atmospheres of our atmosphere, right, is oxygen. And it only takes 0.0 only takes this much to reach 50% occupancy, even though you have this much available in your atmosphere. Ridiculously strong, very high affinity, right? This is like 60 times, right? 60 times the number of 60 times the concentration required, pretty much, if I'm not mistaken. I could have done my math wrong there, but it's a lot, right? And so you can see here, all they're doing, right, is that if you're given the PO2 like this, you plug values in, right, and you just solve. So you can see here 98% occupancy, right, at this PO2, right? Over here, this is in the lungs, right? In the tissue, right, instead, it's 94% occupancy, right? So it hasn't dropped by that much. All this to say, the tissue, right, has a lot less O2 near it than the lungs. The lungs are what to provide O2, and the tissue uses up O2, right? But myoglobin still holds on to O2 very strongly, even in the tissue, even though there's less O2 there, right? Like significantly less O2, right? Like 1/3 the O2 in the tissue than there is in the lungs, and it still holds on to it really strongly. That tells you that it's probably not the best idea to try and use myoglobin as an oxygen carrier, because your tissues need the oxygen. And if you're holding the oxygen with myoglobin, it's not being used by the tissue. And so here's the binding curve, right? You can tell it reaches this point very, very fast, right? So, yeah. Let's look at hemoglobin instead, right? So hemoglobin's function released through, all right? We'll look at this and this again, right? If we design this new MB that dissociates, right? How does this work, right? So here we go. Let's change the P50 to 4, right? Before it was 0.26. Let's change it to 4, much higher, right? Now it's different, right? Now we've got much less occupancy and much less occupancy in the tissue, right? This is probably better, but this is quite weak. It doesn't bind that much in the lungs, but we want it to bind more in the lungs, right? And we want it to release more in the tissue, right? So that's not great. It's okay, but it's definitely getting there, right? Similarly, right, if you keep changing it, right? Notice how we're changing this KD value, right, or this P50 value, and this denominator is getting larger, and the occupancy is getting smaller and smaller, right? That's the importance, right? You make this number bigger and bigger, right? It now takes more it now takes more oxygen to actually reach. It actually just lower. It takes more oxygen to reach the same uh, occupancy, right? So this is the higher P50 value, right? And you can see that compared to here, right, where the P50 value is lower, the occupancy is now much lower, right? Okay, so how did nature solve this issue? Because if we just keep messing with this and changing it, the P50 so it's bigger, it just gets worse at both, right? It gets worse at absorbing O2, but it does get better at releasing O2. But we need to be good at this and good at this, right? So we need to do both. We made hemoglobin. Hemoglobin is 4 polypeptides. It is a quaternary structure with 2 alpha subunits and 2 beta subunits, not 2 alpha helices and 2 beta sheets. The subunits are called alpha and beta, and they're made of combinations of alpha helices and beta sheets, right? Here we have cooperativity, which is the idea that the binding of one ligand alters the affinity for other ligands, subsequent ligands to bind. You can see here that myoglobin, right, is used as a storage molecule for O2. So it's actually used in things like muscles, if I'm not mistaken. And hemoglobin is used as a delivery molecule. It's used to deliver protein. It's used to deliver oxygen to tissue, right? Here we see that unlike myoglobin, the binding is hyperbolic, right? You can see here that if we look here, right, the idea is that the P50 for myoglobin is here and the P50 for hemoglobin is here, right? This is obviously much higher for myoglobin than hemoglobin. But you can see, right, that if we get up to these like 8 kilopascals, right, we have very, very, very high affinity, right? There's a very high affinity for hemoglobin here, right? Relatively high. Likewise, if we go lower down, there is a lower affinity, right, in this region, right? And up here, right? This allows for high affinity and high binding of O2, right? But also allows for very high release of O2, right? When we're in the tissue, right? So if we compare, let's compare real quick, right? So if we look at the PO2 in the lungs, right? Myoglobin and hemoglobin, right, have about the same occupancy. Hemoglobin is a little bit lower, right? But it's about the same. However, if you look at in the tissue, right, this area here versus this area here, myoglobin hasn't released anything, right? While hemoglobin's released like 50% of its O2, which is awesome, right? It's releasing its O2 to the tissue while myoglobin's not releasing anything, right? It actually tells you right here, 0.4, right? But the idea here, right, is that this cooperativity, right, allows us to release a lot of O2, unlike myoglobin, which doesn't want to release anything, right? So here we're back to this idea of P50, P50 effective. It's when occupancy is 0.5, right? In this case, it's 4 kilopascals, right? If we compare it, right, to our design of myoglobin, where we altered the affinity, so it's 4 kPa, like this version right here, right? It's not quite as good, right? So I guess what I'm trying to get across here, right, is that this 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 cooperativity optimizes the binding of hemoglobin so that it's able to bind oxygen, right, in a high affinity way in the lungs, but also release it very easily while it's in the tissue, which is very different from the just if you just had to use myoglobin, right? Myoglobin, if you affect if you change KD, it affects the binding and release, but they both it very drastically. Like the binding becomes super bad while the release becomes super good. But we need it to be able to bind strongly in certain cases and release very well in other cases. So that's why hemoglobin cooperativity makes it a great deliverer of oxygen. So now we have the T and the R state. So the T is the terrible state and the R is the really strong state. So you just have to remember that. They spelled terrible wrong. Funny. Um, But yeah, the idea, right, is that it can exist in different states, the T state and the R state. And the T state, right, is the state that's just really bad, right? There's very little binding, right? And the R state is where we get a lot of really strong binding and good release, right? So these amounts of T and R state will actually change with increasing or decreasing PO2, right? So the total hemoglobin concentration is equal to the total hemoglobin in the T state and the R state combined. I don't think there's really anything else in this section that I want to talk about. And really, I think this is important. This right here, right? What you should know is that as PO2 increases, the amount of hemoglobin in the R state increases, right? While the amount of hemoglobin in the T state decreases, right? And so the P50 effective drops, meaning that the affinity for hemoglobin for oxygen goes up. So the R state, right? So the R promotes decreased P50, right? Which promotes increased O2 binding. You can imagine the opposite for T, right? So T state, right, promotes high P50, which promotes decreased O2 binding, right? This is what you should keep in mind, right? And then different things can cause this R and T state. So the oxygen binding causes the R state, right? While things like carbon dioxide, carbon monoxide, like acidosis, these things cause the T state. And here's just another so for things that are cooperative, right? We can't just use the same old Ligand equation, so we have to use something like this instead, right? For something like hemoglobin, right? You'd obviously still use P50 here and like the PO2, right, in these sections here instead of the L, right? But the N value is the number of binding sites. So for something like myoglobin that only has one binding site, it's hyperbolic. You just put 1 here and L to the power of 1 is just L, right? But if you have something like hemoglobin where it's 4, you have to multiply this and this value by 4. This is something to keep in mind, right? Sometimes they'll ask you things about like having 2 binding sites, maybe 4 binding sites, right? They'll usually try and make the numbers easy to work with if they do that. But just be very careful when reading the questions to make sure that they talk about that if they do talk about things like enzymes or proteins, that you're not looking at something that has cooperative binding. And if it does have cooperative binding, look for how many binding sites it has, because that does matter quite a lot. um this is just a way of kind of showing how cooperativity works, right? So like here, right, so you have this protein, right, you have some number of ligands, right, and then this K1, you have binding of one ligand, right, there's some extra ligands, and then you find more ligands, and then you keep binding more ligands, right? Basically it's infinite, depending on, well, not infinite, but depends on the number of binding sites there are, right? Yeah, here's this idea here, and this basically tells you the degree of cooperativity, right? So N tells you how cooperative something is, right? If N is greater than 1, right, you can say that something it has positive cooperativity. So the binding of one thing positively affects the binding of another. So it'll increase the affinity for the binding of another ligand, right? If N is equal to 1, hyperbolic, there's no cooperativity. If the number is less than 1, it's actually negatively cooperative. What that means is that the binding of one ligand actually decreases the affinity for the binding of another ligand, right? So that actually looks on a graph, if you were to see that, sigmoidal positive cooperativity looks like this, right? Like sigmoidal, hyperbolic curves, just one binding sites. Generally speaking, negative cooperativity looks very like square. It's very interesting. Let me see so I can find like a good idea. Yeah, so like negative cooperativity would look something like this. Like it would look like that, and just like go straight. It's very weird, right? It looks odd. It like does this thing where it goes, it's not like curved very much, it's like very square. So it like does this, or like maybe like it goes up a little bit. um But just be aware of that. Something they could possibly test on. But I wouldn't be too concerned about it. It's definitely a thing though, so just be aware. This is just kind of showing like, so yes, if you have one ligand and one binding site, just use this, right? N is equal to 1 here, right? So don't change anything. If you have one ligand and independent binding sites, right? So there are multiple binding sites, but they're independent. You still use N equals 1 here because they're independent. They don't influence each other, right? You have one ligand and it's cooperative binding, right? Then N is greater than 1, and you have to change these N values to be whatever the number of binding sites is. Other than that, or anything else? Yeah, in this case, it's very highly cooperative. N equals 3 here, right? Yeah, so in this case, yeah, so I mean, like, if you look at this, right, so, like, for the, you go from 10%, like, something like here, right, to 90%. The change in ligand, right, goes from, like, what? Probably, like, 2 to 6 or kilopascals, right? So, the cooperative binding does have an effect on it, right? If you look at this one right here, right, to go to like 80% bind, you don't even see it here, right? It's like for this low affinity one, you don't even see the 80% point. It's too far to the right, right? Over here, if you look at it for this high affinity state, right, it's too quick, right? So like 10% is like right here, right? And 90% is also like right here. There's no difference. So other than that, I don't think there's really much else to know about this. I think the main thing you should take away from this is that hemoglobin has cooperative binding. There are 4 binding sites. N is equal to 3 in this case. I want to double check that actually. I don't. Is that correct? I think it should be. Oh no. Okay. Yeah. 3.1. Yeah. Okay. Yeah. So yeah. So in this case, the binding of hemoglobin here is 3, right? Um, just keep in mind that this can change for any given protein, right? They should hopefully tell you, right? It'll tell you like the number of binding sites, or they'll tell you the number, right? Um, but just be aware of that, right? So yeah. I think what I also want to stress as well is this differentiation, right? So notice how it's like degree of cooperativity versus sites. It's a bit weird, but I would just be careful, right? So like for here, it's using lowercase n, so degree of cooperativity, right? So the number of binding sites for hemoglobin is 4, but the degree of cooperativity is is like 3, right? So be aware that sometimes there is a difference between these. So don't just blindly assume that if there's 4 binding sites, that there's the lowercase n values can also be 4. If you have a question like that, make sure you confirm with like whoever's teaching, like the professor or the or TA when you're taking the exam, what they want. If you get a question like that, right? It's always better to make sure because these values are slightly different, right? Or they can be slightly different, right? Even though they're equations. Just be aware of that. Um, Other than that, I think that's all I have for this video. It's again more of a short video. I think there's not really much to cover for these, right? But hopefully this video was helpful. If it was, great. If it wasn't, ouch. But yeah, have a good day, everybody, and happy studying.